What if the next great technological breakthrough isn't just overhyped, but potentially destabilizing for the world? It may also break encryption, upend financial systems, and concentrate power in ways we've never seen before. So is this the next revolution, or is it just the next narrative?
Quantum mechanics would say, no, not really, until you do the knocking, and that's a measurement. The table doesn't exist. This idea that you can have one theory that really is the description of the world is really more of a dream than a reality.
The deeper we go, the more complex this whole idea becomes. The more we discover, the more I think we realize we don't know. What if the next great technological breakthrough isn't just overhyped, but potentially destabilizing for the world? Well, quantum computing promises to solve problems beyond the reach of today's machines, but it may also break encryption, upend financial systems, and concentrate power in ways we've never seen before. So is this the next revolution, or is it just the next narrative? Well, there's a really familiar rhythm to technological progress. Gartner calls it the hype cycle. We see a breakthrough emerging, or at least the promise of one. Capital floods in, narratives are constructed, and somewhere between genuine innovation and a bit of market storytelling, a kind of mythology begins to take hold. And we've seen it before, from the early optimism of the internet to the promise of blockchain as a decentralized utopia to the more recent fervour around artificial intelligence. Each wave has carried both real progress and, I think, a degree of narrative inflation. And now once again the spotlight turns to quantum computing. It's touted as the next great leap, a technology that could solve problems beyond the reach of our classical computers of today, and it's increasingly being framed, and I think perhaps conveniently, as the next frontier, just as cracks begin to appear in the current AI narrative. So we're going to go beneath the headlines and the hype and to find out exactly what is going on with quantum computing, because here again the echoes of The Spell, the book by David Buckham and Robin Wilkinson, are clear. Just as nuclear physics evolved from abstract theory into a force that reshaped geopolitics, often faster than institutions, I think, could adapt, quantum computing, I think, may be following a similar trajectory. Well, to help us with that, I'm joined by Andrew Forbes, a distinguished professor of physics at the Wits University, founder of the Structured Light Laboratory, and a central figure in shaping South Africa's quantum strategy. His work sits at the cutting edge of photonics and quantum optics, from pioneering programmable digital lasers to advanced high-dimensional quantum systems that could underpin future quantum communication and computing architectures. So it's a lot to take in. Professor, welcome. It's really great to have you on the podcast. I'm sure I didn't get everything in your CV in there, but just take us back to how you became so enmeshed and involved and superimposed, if you'll allow me, in the world of quantum physics.
No, thank you very much for having me here, and it's a fantastic summary. I should employ you as my publicity agent. No, fantastic. Look, I guess our entry has been a rather long one. So we've started off in photonics, so that is playing with light and light-based technologies. And of course, these technologies have anyway become revolutionary. If you think back 20, 30, 40 years ago, your television would be a big tube. You'd be speaking to people over the telephone with copper wires connecting one another. Today it's all light-based. So we've seen light-based technologies drive this new revolution around the globe. And they're the driving force behind quantum technologies too. All the early experiments were done with photons, the particles of light. And so it's not surprising that becomes the bedrock on which we're basing much of our quantum technology today.
So what is quantum physics really about in lay terms? What do people most commonly misunderstand about it?
Most people think it's some magical principle or box that allows you to do anything out of the ordinary. That's not really true. At some level, it's a little bit mundane. When I speak to my students in the lab, I always say to them, isn't it amazing that the theory does this? And they're like, no, that's not amazing. That's what the theory says. What is it really? What do people not understand? I guess it's this two parts to it. The one is the very small. It tries to describe the very small and the fact that we don't live in a continuous world. Rather than a smooth slope, we have little staircases, so you can only go in finite steps. This is very unusual. You think that you can smoothly landscape anything you want. Turns out that's not possible. And the other side of the theory is this notion of entanglement, that we can get things connected in a way that kind of defies common sense, appears to violate some of the things we believe are true in the world, that, for example, there's a reality behind things. If I knock on the table's really here. Quantum mechanics would say, no, not really, until you do the knocking, and that's a measurement, the table doesn't exist. So these are very unusual properties that kind of makes you think a little bit differently, and I think the public don't quite get that. They get all the hype and the science fiction, but maybe not the science.
Yeah, well, and it's kind of understandable when you're asking someone to think that something only exists once you interact with it by knocking on a table, for example. And I've always, the idea that things can exist in two different places at once simultaneously, kind of like Schrodinger's cat. I think, again, it's a bit mind-bending for many people. For over a century, I think physics has been shaped by two extraordinary frameworks. So you've got quantum mechanics and you've got general relativity. And yet, despite their success, these two theories remain fundamentally incompatible, leaving us without a complete picture of what reality is. Why are our current understandings of quantum mechanics and gravity currently unreconcilable?
The bedrock on which they're based is very different. Quantum mechanics assumes a certain space-time, a certain way that how things connect in the world. And that is completely in contradiction with how general relativity does it. So the idea that things can be curved and that masses could interact with it, that doesn't exist in the quantum world. The quantum world is really it's a wave theory, and general relativity is definitely not a wave theory. That's a very technical answer. I think maybe the less technical answer is that, and maybe slightly controversial, would be that, why should they merge together? I mean, in physics, we would say that, or at least I would say that, a theory is there to make predictions and to understand the world, and the theory is only as good as the thing you want to predict. If I want to predict the temperature change of my body, then a theory that treats me as a cylinder of water is very, very accurate. If I want a theory that describes the way I think and live and feel, a model that treats me as a cylinder of water is a terrible theory. So theories can be both very, very good or very, very bad, depending on how you want to use them. And this idea that you can have one theory that really is a description of the world is really more of a dream than a reality, I would say.
And that brings me to this idea of a theory of everything that could reconcile quantum mechanics with our current understanding of gravity. And it's been a long-standing ambition in physics. Do physicists still broadly believe in that, or is that confidence fading?
I think it's a hope. I would put it borderline religion. It's something that we hope is true. We want to believe it's true. And that belief is based on early successes, that we were able to group things together that seemed very disparate. Galileo dropped balls off the Leaning Tower of Pisa. That seems a very particular type of experiment, but we could link that to the way planets move, the way balls roll on slopes, the way light bends around stars. It's amazing that we could group all these seemingly very different things and put them under one theory. So physics aims for elegance and simplicity, and the most elegant and simple thing would be to have one theory that describes all. But that doesn't mean that that is the reality or that that would be a useful theory. So we hope that we can keep elevating what we can understand rather than say God designed it all, but say these are the underlying principles that govern the world that we live in. But whether that's possible or not is very much an open question, and definitely I think people are getting a little bit jaded in their view on that.
The more we discover, the more I think we realize we don't know, and the more complex things seem to become. And so we've made extraordinary progress, yet in many ways it does seem the deeper we go, the more complex this whole idea becomes of trying to develop a general theory of everything. But among the major approaches, we've had string theory, we've had loop quantum gravity. Which, if any, do you find most compelling?
I don't find any of them compelling, to be honest. I really think I think it's Penrose who said that perhaps it's just an onion, and you peel off one layer and you find another layer underneath it, and you peel that layer off and you find another layer underneath it. I really think this is the reality. And presently, if I look at a good theory makes predictions. With my cylinder of water as a model of my body, it can make very accurate predictions on how my temperature would change. It would make any predictions on how I would think or feel.
Mm.
And the present theories, from what I can see, looking from the outside in, although I'm a physicist, this is a very specialized direction that people take. I don't see any concrete predictions that are not already covered in existing theories. So there's no go and look here, I predict something that you would not have thought possible. I don't see those stark tests out there, and therefore for me that means that the theories are kind of patchworks and not really adding a lot of value to what we already have.
Right. So I think I'll understand exactly what you think of whether or not we're moving closer to complete understanding of reality. Probably not. But let's talk specifically now about quantum computing. Because this idea that you have qubits and they can both exist in different places simultaneously, I think is fantastic. Maybe you could try and simplify it in lay terms as well, how some of the features of quantum physics are being harnessed to build these new technologies like quantum computing.
Yes, quantum computing leverages off principles of superpositions. And embedded in that is this idea of entanglement that the public would definitely have heard. What is the essence of it? Entanglement, the essence is essentially that you can have two particles, doesn't matter what they are. They could be particles of light, or they could be electrons, or in Schrödinger's example, as you said, they could be cats. But you have two particles that are connected, and this connectedness is beyond what we would experience in the classical world. So it means that a measurement on one affects the outcome on the other one. Now, in the classical world, we do have that. It's called a correlated outcome or conditional probability. If I have two balls in my hands, one is red and one is blue, and I put them behind my back and I say, pick a hand, and I reveal a blue ball, well, then you know for sure the other one is red. So this we know very well. What makes quantum strange is that it must exist across any choice of measurement you make. This is very strange. It means that I should be able to pull out a ball that is half red and half blue, and then the other one must also be half red and half blue. This is now very strange, this idea that it must exist regardless of what I choose to measure. This we can harness to do all sorts of cool things, from imaging to communication. What computing leverages on is the fact that we can treat all of these correlations as waves, including the particles themselves. So what is cool about a wave? Well, if you ever watch waves and I put an obstacle in their path, they simply go around it. In the quantum world, if I put a particle into a maze and I say, try to find your way through this maze, if it was a classical particle, at every junction it would choose, shall I go left or shall I go right? Make a decision, and perhaps it's the wrong one, and you come to a dead end, you have to start again. So it takes a very long time to get through the maze. In the quantum world, because the particle can treat itself as a wave, it can go left and right at the same time. And then when it hits the next junction, it can go left and right at the same time. And so its ability to spread out and get to the edges faster is the essence of the wave nature of the way these paths interact. This you don't see in the classical world. And this really is what we leverage on in the quantum world, specifically for quantum computing.
So how would then that differ from classical computing using ones and zeros? Because I think people often assume quantum computers are just faster. Is that the right way to think about them, or is their power fundamentally different given that they are operating like waves rather than, traditional particles?
It's more that because they can hold a superposition, this means that they can hold the 0 and the 1 and any combination thereof simultaneously. In the classical world, it's a 0 or a 1. The switch is either up or it's down. In the quantum world, because you're allowed to have any measurement basis you choose, in simple language, this means the switch could be up, could be down, could be halfway or 3/4 or any combination. So there's an enormous information capacity. So the benefit of quantum computing specifically is that because the information scales exponentially, in a classical world, a classical computer, the resources that you need to solve a problem scale exponentially. You need more and more resources to solve a difficult problem. In the quantum world, that's also true, but the information also scales exponentially. So they kind of cancel one another out. And that's why quantum computers, for the same resource, can do so much more. It's not that they would need less resources to solve really big problems. It's just that they have the scalability that kind of cancels so that you can get more bang for your buck, essentially. And that resource is the fact that the information capacity is just so high.
And hence the great excitement around what we can use these specific quantum computers for in terms of medical research and genomics and that kind of thing, where there is just a vast amount of data. Cryptography is another one, and on the flip side, I mean, there's a big, obviously, security concern. If we can crack current cryptography using these computers, there's obviously a lot of excitement around quantum at the moment, but I think also quite divergent views on how close we are to really making it practically viable. You've got companies like Microsoft, IBM, I think even Google. They've suggested timelines of years rather than decades. NVIDIA's Jensen Huang, I think he's on a far more cautious view. I think he reckons we're 20 to 30 years away. From your perspective, how close are we really?
It's extremely difficult to say. On the one hand, if I look at the roadmaps towards a quantum computer, and there's several of them, so some of them are based on trapped ions, some of them are based on trapping atoms, some of them are based on superconducting qubits. Think of this as more like the electronics that we might use today. Some of them are based on particles of light, photonics on a chip. They all have very different technical challenges, and if I were to be asked to put money on which one would win, I really wouldn't be able to say. My gut feel is that solutions that involve trapping ions and atoms, that just seems too complicated. The superconducting qubits, very mature technology, but the challenge of noise in material systems is very, very high. It's really a serious challenge, and I have not yet seen any paradigm shift in how that would be solved. Photonic solution is a bit of a dark horse. Jeremy O'Brien left Bristol University, has raised billions of dollars to start up a on-chip photonic quantum computer, promising 10,000 qubits within the next couple of years, but revealing nothing on the status and the progress, although Queensland are building a quantum computing factory, so investing $1 billion Australian dollars. So whether he will make it, and he's got something in the background that he's just not telling us yet, time will tell. I don't think we'll see quantum computers work. Let's begin there. They already work. You can access a quantum computer on the cloud. You can run your algorithm. The only issue is that they don't do any better than a classical computer. So when I was a student, if you'd asked me, would a quantum computer eventually work one day, I probably would have said no. Seems too far-fetched. Today they work. As you said yourself, when you think of all the leaders in quantum communication and quantum imaging, it's all top universities that would roll off your tongue. If you ask to list the leaders in quantum computing, it's all large companies. That means that the pace at which things get done and the focus is vastly different. So on the one hand, I see the promise, big companies investing a lot of money with very good people who have to deliver. That surely will make them focused on the solution. On the negative, I see all the challenges and no paradigm shifting way of thinking that will jump us over the noise hurdle. So it's very much still a gamble, I would say. And gamblers, would it be able to do what we believe it can eventually do?
Right. But I mean, just the fact that, as you said, that we've got a quantum computer to work, and in your lifetime, when you were a student, you probably would have thought that would have been too far-fetched. Just shows you what can be achieved.
Definitely.
What is the noise? What is the noise problem in particular that now needs to be solved for in order for us to make that leap, that next leap?
For a long time, the community, that's mostly professors, I guess, have been telling the companies, we don't need more qubits. These would be the quantum equivalent of a bit in your electronic chip on your computer. We don't need more qubits. What we need are more useful qubits. And if you were to look at, for example, the IBM roadmap, which they tell you where they're going in the forthcoming years, if you were to go back a few years, you'd see that it was very much along the lines of, we're going to increase the number of qubits every year, and we go from 100 to 200 to 500 to 1,000 and so on. Last year, they reversed that. Said, okay, we're not going to try to increase the number of qubits. We're going to try to maintain it and start to look at the noise issue and make them more useful. So the problem is that with material things in the world, like the table, I can interact with the table very easily. I can touch it, I can feel it, and so on. The same in the quantum world. When you have material particles, they feel the environment much more acutely than, for example, light would do. Light can fly around without feeling anything. And in the quantum world, when you interact with your environment, the world around you, the quantumness tends to decrease in general. And this makes the qubits less useful. And that's why when you look at a quantum computer and you see this very large, very coppery type structure, what you're really seeing is the fridge. And the computer is just a tiny little chip. The rest of it is just a cooling system to try to keep it away from the real world and make it as noise-free as possible. That isn't really the computer. That's the fridge behind the computer. So until we can get around that, we may have many qubits, but we don't have many useful qubits. And right now we have about one useful qubit for every 1,000 real qubits. And that's a terrible statistic. And it means that we can't do anything useful at the moment with quantum computers.
And does that speak to the inherent instability of qubits as well? I believe that's also been a problem when it comes to scaling this technology, and that qubits are in an environment where they are interacting with other particles inherently unstable.
That's right. If you base your quantum computing technology on things like electrons or energy levels in atoms or ions, you're always going to have this problem. PsiQuantum, Jeremy O'Brien's company, have promised to go the photonic route on the basis that light doesn't have this problem. Photons, or particles of light, don't interact with the environment, and so you essentially can get over the noise problem. But of course, light is, you said, well, then why isn't everybody building quantum computers based on light? Well, light tends to move very fast, and would prefer to have things static if you're going to do computations with them. So the idea that the particles move around at the speed of light is highly inconvenient. So that has its own technical challenges. So in all the roadmaps, we have challenges. But in the present mature technologies, it is noise as the number one challenge.
I've got to ask you, for those on the outside who might be rather cynical, jaundiced, call it what you will, to what extent is the current narrative around quantum computing justified versus overhyped, maybe in a way similar to what we've seen with the early promises of AI and other technologies in the past?
I think there are many voices in the community, and certainly there are some very loud voices that are pushing the hype. But I think there are just as many sensible voices that are not. We, in our community in South Africa, we have given access to quantum computers to our researchers and to industry that want to work with us. And what I tell them always is, look, it's not going to do any better than your classical computer. All the research papers that claim a quantum advantage have been those problems have been very carefully constructed in order to show this advantage. If you were to pick an obvious arbitrary problem, there would be no advantage. But I tell the private sector, just come and play. I think you should be an intelligent user. You should be an intelligent buyer. You should be if you're going to make a decision, making an intelligent decision by understanding what the technology can and can't do. So my advice is go and play on a quantum computer. You can play for free on the cloud. Go and play with it. See what it can and can't do. Learn for yourself. Watch the trajectory of the technology as it matures. And if it comes true, fantastic. You'll be in a great place to exploit it. And if it doesn't, well, you understood what it couldn't do, and you've gained from that too.
I think it's a very pragmatic view that. But once achieved, what kinds of problems is quantum computing genuinely well suited to solving, and where is it unlikely to help? I mean, I don't see a quantum computer being, particularly useful in a cell phone, for example. But where do you see quantum computing making the big impact?
Certainly, quantum computers are not going to replace our classical computers. It's not a disruptive technology in that sense. We're always going to run Excel calculations on our little computers. We don't need quantum for that. So the solution in the end will be a hybrid solution where you won't know whether the algorithm that you're running has been passed to a classical machine or a quantum machine. It may go through both, some parts on one and some parts on the other. Where would the quantum computer have the biggest impact? Let me go back to the example with the maze. And I'll turn the problem around. If your listeners have ever played on a pinball machine and you drop a ball, it bounces around and it lands at the bottom, and it mostly lands in the middle, and occasionally it might bounce to one of the edges, but mostly it goes kind of randomly but down the center. The quantum ball, if you were to drop it, because of the way the interference and superpositions work, they're more likely to end up on the edges and less likely to end up in the middle. And you might say, well, how is that relevant to computing? Imagine that you have a very large space that you want to search. It doesn't matter if it's a database or an optimization problem with many possible solutions. Imagine a very large space and you want to get to the edges of the space faster. With the classical routes of computing, it's very hard to get there because mostly you're in the middle and the tail off gives you a very, very small probability of getting to the edges. So you need to push up your resources to get farther away from the center. The quantum computer gets there naturally. And so this is the big benefit. Any problem that requires searching big spaces, whether they're, as I said, databases, or as you said, pharmaceutical problems, where there are many, many proteins that could be added to give the functionality you wanted, or logistical problems, anywhere where the solution space is very big, quantum computers will have an advantage.
On the flip side, is it, a lot of people are worried that it could invalidate our current encryption, undoing data security, for example, behind banking, or is that a real concern for you in terms of a potential negative implication?
It definitely is. That is another example of a very large solution space. So in very simple terms, our encryption today is on the factorization of prime numbers. I give you a very large number and ask you to find the factors. This is a slow, tedious process of going through all the possibilities that might work. And quantum computers will do that very, very efficiently. Shor's algorithm will solve that in real time. We're very far from having that. We need about 10,000 useful qubits to do that. So we're very, very far from that. But in principle, the quantum computer can do that problem very efficiently. What would it require to address? NIST have been looking at post-quantum algorithms. Essentially, the trick is to change the mathematical problem to one where you're not looking for this factorization and pick the problem that the quantum computer is not good at. And there are many problems where it isn't good at anything. It wouldn't give you any advantage over your classical machine. So it definitely is not a silver bullet that solves all problems. It solves particular problems very, very well. And if we make it work, the hybrid solution of classical and quantum can be enormously powerful.
It will mean just that the current security systems will have to adapt and play in areas where quantum computers are not as strong, as you say. Can you tell us a little bit more about the work that you are doing with WITS-Q and the WITS Structured Light Laboratory? What research is being conducted there, and where does all of this then fit into the broader goals being pursued in quantum science?
So South Africa has a national quantum strategy, and we're, I believe, the only country in Africa that has such a strategy. So we have particular directions. We don't have a lot of resources, so we have to be very careful where we put our chips, and we've decided to put them down on quantum computing. But there, the emphasis is not, in our strategy says we will not build a quantum computer. We will work on quantum software. So, you don't have to be part of the, you don't have to make smartphones to be part of the smartphone economy. Yeah. You can make apps that run on smartphones. So that's one direction. The other is quantum imaging and sensing. We have a strong metrology center in South Africa. We believe there's enormous benefits in industry to look at how we can harness quantum for sensing and gathering data better, and quantum communication, so securely transmitting data. So both the national strategy and what we do in our lab, which is aligned with the national strategy, is data-centric. It's how do you gather data in new ways, which would be imaging and sensing. How do you transport data in new ways, which would be quantum communication. And then it's how do you process data in new ways, which is quantum software. So those are also the three directions that we're pursuing in our own lab.
Fascinating. And, you mentioned photonics as one of those options when it comes to, the directions that the community is taking this technology. And I think your research often sits at the boundary between classical and quantum optics. Do you see it obviously as is it a continuum, or is there still a meaningful divide between the two worlds?
Now here my view is again slightly controversial, although I must say less so these days. Quantum mechanics is fundamentally a wave theory. So if you pick up a quantum textbook as a student, it might even call it wave mechanics. And, we already have a wave theory in classical physics. It describes light and sound and many other wave systems. And so the idea that these are two separate theories is simply not true. There is a very strong overlap in the middle. And in fact, I can make classical systems behave as if they were quantum by simply looking at what property is really being utilized for the quantum resource. So for example, the idea of this particle falling down the pinball machine, I can make that particle look like it's quantum by simply using waves rather than a physical particle. Because this quantum walk, is nothing more than a superposition of waves, and we have waves in classical physics. So I believe there's a very large middle region where you could benefit from both worlds. And we're very lucky to work in both worlds, and we do look for those benefits.
And it's a compelling argument, even to a layperson such as me, when you explain it like that. Just as we reaching the end of our time, Prof, I think when we look at a lot of incentives out there, and I want to be a bit provocative now, to what extent do you think big tech and the incentives there, particularly the need to justify these high valuations around some of these big tech Mag 7 type stocks, are shaping the public narrative currently around quantum?
Yes, I mean, when people raise very significant funding, the hype only gets you so far, and eventually people want to see deliverables. And I think if you focus on show me the true quantum advantage, it's still very much in the early stages. Definitely in the science labs, we can show the potential, we can show an advantage, but in the technology, not yet. When we go and speak to industry and we try to tell them what quantum imaging can do, then they're like, well, great, I'd love to buy a quantum camera. And then we have to say, oh, sorry, quantum cameras are still very much at a development stage. They're not yet at the level that they can do something practical. But my message to the skeptics would be, look, the technology that you develop in moving towards quantum, that in itself is very useful. So in our lab, we have a spin-out company, for instance, that we call it quantum-inspired technology. So what's inside the box is not quantum, actually, but that wouldn't be possible if we hadn't been working on quantum technology. So while we push the maturity of the technology we really want to see out there, there's a lot of value in the chain and the kind of path that you've walked that can make a difference to society.
Yeah.
So I would say don't discount the value of quantum-inspired solutions, but be careful that you don't put all your money on a bet that may not realize in the future.
And just finally, given South Africa's quantum roadmap, and I'm sure your involvement in advising on developing that, are we investing in the substance and ensuring that we're not being swept up in some of the global hype cycles? What do you think about the direction of travel for South Africa when it comes to our own, quantum path?
So I should declare that I am definitely biased, since I am the director of the program and help write the strategy. But I believe that we've been very sensible about it. Look, we have a very small quantum community. We have very limited resources. We had to think really carefully how we could spend our money. And let's take the quantum computing argument. We made a conscious decision not to build a quantum computer. We can't afford it. We don't have the people. And even if we did, we're just too far behind the game. And so I think the decision to invest in software where the entry barrier is much lower, the cost is lower, and we have lots of fantastic IT people that can make quantum agnostic software that works regardless of what machine eventually wins the race, whether it's the IBM or the Getty or the PsiQuantum, the software should still run. So I think this is a very sensible strategy for a country with limited resources. And I think that's, what's the worst case scenario? Quantum computers never do anything useful. Well, then we'll train some software engineers. That's not the end of the world. They do something useful. Fantastic. We have the beginnings of a quantum software industry. So I think we've made sensible decisions, and I think we're making excellent progress towards our goal of a quantum workforce and a quantum economy.
Well, Andrew Forbes, thank you very much. Distinguished Professor of Physics at WITS and founder of the Structured Light Lab, and as you said, a central figure in shaping South Africa's quantum strategy. Thank you so much for helping us, Joe Public and Jane Public, understand a little more about this fascinating and strange science of quantum and quantum computing here on the Under the Spell podcast. Been a great pleasure sharing your time.
Thank you very much.